Why waste time in commute and spend lot of money for iitjee coaching? Parents, do you want your kids to achieve top scores in iitjee? India's leading online NEET coaching 100% success iitjee. At TeenEinstein, we focus on iitjee coaching from class 6 to class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for class 6 to class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.
Everyone, in the previous lecture we talked about electrostatic potential and potential energy, potential of a point charge and dipoles and everything. In this video we are going to talk about electrostatics of conductors. So we are going to see the properties of conductors with respect to electrostatic conditions. So the first point which we are going to see is the electrostatic field is zero inside a conductor. So why electrostatic field has to be zero inside a conductor? So if we can assume that electrostatic field is not zero, then what will happen? Whenever there is an electrostatic field, there will be a force associated with it. So this is a conductor. So conductor means it will have free electrons. So the electrons will be free to move everywhere. So if there are electrons inside the conductor free to move everywhere, and there is an electrostatic field inside the conductor, then the electrons will be moving, or the charges will be moving here and there because of the field present. So it will not be an electrostatic condition anymore. So in an electrostatic condition, the electric field inside a conductor has to be zero. The next point is, at the surface of the charged conductor, the electrostatic field is always normal to the surface at every point. So like it's shown here, there is electrostatic field coming out of the conductor, but it has to be always normal to the conductor. What if it's not normal? What if it makes an angle with the surface of the conductor? Then what will happen? If it makes an angle with the conductor, it will have two components, perpendicular component and the horizontal component. The horizontal component will be acting along the surface. So if there is a component of electric field along the surface, the charges can still move along the surface. So then this is not possible. So the electrostatic field has to have only perpendicular component. Even if it has a component along the surface, the charges will move and cancel the field. So this is also true. The third point is, the interior of a conductor can have no excess charges in the static condition. Why is it so? We already talked about this. So the electrons or the free charges which are inside the conductor are free to move, right? So if there are a group of charges inside the conductor, they will try to be maintaining as a maximum distance as possible within the conductor. So that's why they always go to the surface. So the interior of the conductor, there cannot be any excess charges. If there are excess charges, they move to the surface of the conductor. The fourth point is, electrostatic potential is constant throughout the volume of the conductor and on its surface. So this is also true because electrostatic field inside the conductor is zero. When the field is zero, then it means that the potential difference have to be zero. So if the potential difference is zero, it means that throughout the conductor, the surface or volume, everywhere, the electrostatic potential has to be zero. In other words, if you want to move a charge within the conductor or on its surface, anywhere within the conductor, you don't have to do any work because it is on the same potential. In other words, we can also say that conductor is like an equipotential surface. Okay. The last point is the electric field at the surface of the charged conductor. We can find out what is the electric field at the surface of the charged conductor by using Gauss's law. So we know that E equal to sigma by epsilon into n cap. And what we are going to do is we are going to construct a Gaussian surface here, and here we have constructed a cylindrical surface. And there are many surfaces. One is the circle here, and the bottom circle here, and there is a curved surface here. But since it has only outward normal component, we can ignore all the other surfaces and find out the total flux only for this surface. So the total flux for this surface is E multiplied by delta S, which is equal to Q by epsilon 0 according to Gauss's law. What is Q? Q is nothing but the surface charge density multiplied by the surface area. So surface charge density multiplied by the surface area delta S divided by epsilon 0. So this is Gauss's law. So this gives us the meaning E equal to sigma by epsilon 0. So this is the electric field at the surface of a charged conductor. Okay. Then we will see what is electrostatic shielding. So a conductor with a cavity with no charges inside is shown in the figure. The electric field inside the cavity is always zero, whatever may be the size and shape of the cavity, and whatever be the charge on the conductor and the external fields in which it might be placed. So for example, we have a conductor like this and there is a cavity inside. There are no excess charges inside this cavity, but there are charges on the surface of this particular conductor. Now you can keep this conductor in any electric field, but inside this cavity the electric field will not be seen. So the electric field inside this cavity is going to be zero. So the metal is going to get affected because of the electric field. The charges are going to move. For example, if you keep this metal in an electric field, the charges will move in opposite directions. They will try to polarize because of the electric field. But inside this cavity, the electric field will not be seen. So it is equal to zero. So that is what this point says. And any cavity in a conductor remains shielded from the external electric field. So this particular phenomenon is called electrostatic shielding. For example, you have a cavity here. You can keep anything inside this cavity. That object will not experience any field. So in a way, you are protecting that object from any external electrostatic field. So this is called electrostatic shielding. Okay, so we are going to see all the points which we talked about now. So in the first point, this is a conductor. If this is a conductor, inside this conductor, rho equal to 0. So the rho is volume charge density. There is no charges, excess charges inside, and the electrostatic field inside the conductor is going to be 0. And even if there are charges, the charges will be at the surface. So plus is here, minus is here. So the charges will move to the surface. And when there is electric field at the surface, they will make 90° with the surface of the conductor. There will be only normal component. There won't be any horizontal or horizontal component along the surface. And V equals to V0 everywhere in the conductor, surface or inside the volume. So metal has equal potential everywhere. And this is the final case where electrostatic shielding is explained. So inside a cavity, the electric field is equal to 0, and when sigma is equal to 0, sigma is the charge density in the surface of the cavity. So this sums up the electrostatic properties of conductors. Next, we will see dielectrics and polarization. So far we talked about conductors and what happens to conductors when we keep them in a electric field. So in this case, we are going to talk about dielectrics. So when you keep dielectrics in an electric field, what happens to them? That's what we are going to see. So the free charge carriers move and the charge distribution adjusts itself in such a way that the induced field is opposite to the applied field. So this is the case of a conductor. So this happens until the net electrostatic field inside the conductor is 0. So when you keep a conductor inside electrostatic field, the free charge carriers will move. They move in such a way that they cancel out the external electric field. For example, this is E0 is the external electric field, and we keep a conductor here. See, the negative charges move towards the left and the positive charges move towards the right. So there are positive charges here, negative charges here. So from positive to negative, again there will be an electric field which is called E induced. So this is E induced electric field because of the external electric field. And this induced field cancels out the external electric field. So then finally we get E equal to 0 inside a conductor, just like how we discussed in the previous case. And what happens in the case of an insulator? So the external field induces a dipole moment by stretching or reorienting molecules of the dielectric. We will see how these two processes happen. And the net charges on the surface produces a field that opposes the external field. So similar to the conductors, in dielectrics also, there is a charge separation happening. But it is different than the conductor. We will see how it is different. But because of the charge separation, there is an internal field created. But that field is not as big as E0, so it doesn't cancel out E0 exactly like in the case of conductor. But it still opposes. So that is the case of dielectric. Okay. Then we talked about two things when we talked about dielectrics in an electric field. One is it stretches the molecules or it rotates the molecules. We will see in which cases it rotates the molecule, in which cases it stretches the molecules. So we are going to see two things like polar and non-polar molecules. So these are non-polar molecules. When we say non-polar, see both are positive and they are located at the same position, both H atoms. And in this case, O is negative, C is positive. They are located at distances, but it is symmetric. So there is no permanent dipole moment in this case. So when we say permanent dipole moment, we need to have a positive charge and a negative charge separated at a distance. Then it creates a dipole moment. But in the case of non-polar molecules, there is no dipole moment present in this case. So in a non-polar molecule, the centers of the positive and negative charges coincide. Polar molecules are the ones where the positive and negative charges are separated, even when there is no external field. Such molecules have a permanent dipole moment. The non-polar molecule develops an induced dipole moment in the presence of the field. So what do we mean by this? This is a non-polar molecule. If you keep this molecule in an electric field, what happens? The electrons will get attracted towards the field. For example, if the field is from left to right, let's say there is an electric field going from left to right, the electrons will move towards the left and the positive charges will move towards the right. So this creates a dipole moment. So this is called induced dipole moment. So in the case of non-polar molecules, there is an induced dipole moment created because of the field. So there are, in both the cases, then we will have some dipole moment. And if you take the dipole moment per unit volume, we define a quantity called polarization. So polarization means dipole moment per unit volume. Okay. So this is a case of non-polar molecules and polar molecules. So in the case of non-polar molecule, in the absence of the field, if you see, both plus and minus are in the same position. When they are in the same position, there is no permanent dipole moment. So this is the case when E equal to 0. What happens when you apply a field? So in this case, we are applying a field from left to right. So all the negative charges move towards the left and all the positive charges move towards the right. So if you see in this case, there is a permanent dipole moment created because of the applied electric field here in the case of non-polar molecules. So this is how dielectric with non-polar molecule gets polarized. When we say polarized, it means it creates a permanent dipole moment because of the applied field. So what happens in the case of polar molecules? In the case of polar molecules, there is a permanent dipole moment present in all the molecules because the molecules have plus and minus charges separated at a distance already, but they are randomly oriented. So we know the direction of dipole moment is from negative to positive charge, right? So we can say that the direction is from negative to positive charge here, and here it goes up, here it will be downward like this. So there are a lot of dipole moments here and they are all randomly oriented. So if you take any particular volume, the net dipole moment is going to be almost 0. And that's why in the absence of the field, absence of the electric field, even though they have net dipole moment, they have permanent dipole moment, but the net polarization can be 0. But what happens when you apply a field? E equal to non-zero here. So in this case, if the field is from left to right, as we assumed in the previous case, the dipole moments rotates and aligns along the field. So if you take a volume and take the polarization, now it's not 0. So this is how, in this case, actually the electric field stretches the molecules and creates a permanent dipole moment. In this case, the electric field rotates the molecules and creates the permanent dipole moment. In both the cases, the polarization is increasing because of the applied electric field. So this is what happens when you keep a dielectric in a electric field. Okay, we will continue talking about this. So the dipole moment per unit volume is called polarization, and we are defining this polarization as P, and P is directly proportional to E, because how much ever is the strength of the electric field, that will only decide how much is the polarization in the material. Because if the electric field is very strong, it's going to stretch the molecules more, or it's going to rotate more molecules, right? So the P is proportional to E. The proportionality constant which we have here is chi E, which is called electric susceptibility. And okay, so what happens when you keep a dielectric between two parallel plates which exerts a field, and the dielectric gets polarized? So there are two, let's assume that there is a plate here, there is a plate here, and the plates exert a field E here, and because of this the dielectric gets polarized. The polarized dielectric is equivalent to two charged surfaces with induced surface charge densities. So we will see how it is so. So if you have a plate here and another plate here, here it will be positive charges, here it will be negative charges. So because of the field, the dipoles align in this way. If the dielectric already has permanent dipoles, then it aligns in this way. So if you take any volume inside, the positive and negative charges are so close to each other, they cancel out. So the net dipole moment will be, net charges will be zero if you take any volume inside. So the only thing left will be this sheet of charge here with negative charge on it, because it is at the end and there are no positive charges on the left side. If you take the right side, again a sheet of positive charges are left here. So this whole dielectric can be considered as a sheet of negative charges here and a sheet of positive charges here. So that's what this point says. The polarized dielectric is equivalent to two charged surfaces with induced surface charge density. So these are called induced surface charges. The field produced by these surface charges oppose the external field. So why there will be a field? Because this is a sheet of positive charge, this is a sheet of negative charge. So there will be an internal field going from right to left. The total field in the dielectric is thereby reduced from the case when no dielectric is present. The surface charge density plus or minus sigma p arises due to the bound charges, not the free charges, because the charges in the dielectric are not free to move. So these are called the bound charges. Okay. So now we talked about the metals. When we keep a conductor in electric field, what happens? When we keep a dielectric in the electric field, what happens? Now we are going to talk about capacitors. So what are capacitors? We will just take two conductors and we will keep the two conductors nearby each other. And we put one positive charge in one conductor and negative charge in one conductor, and they will be at the surface obviously because these are conductors. So this particular system can be called a capacitor. So you need two conductors, two charged conductors, but opposite to each other and equal and opposite to each other. So the capacitor is a system of two conductors separated by an insulator. In this case, what is the insulator that is separating? The air in between is separating the conductors. So this is a capacitor, and the two conductors can have equal and opposite charge plus and minus q. So if one is at a potential V1 and one is at a potential V2, the potential difference between these two is V1 minus V2. The potential difference V is the work done per unit test charge in taking the charge from one conductor to another. So this is, if this is the potential V1, this is the potential V2. If I want to move one charge from one conductor to other conductor, I need to do this much work. The amount of work, that is the difference between the potentials of V1 and V2. So in this case, V is proportional to Q. So the ratio Q by V is called the capacitance. So we are defining capacitance as Q by V. If C is large, V is small for a given Q. So it means that if the conductor configuration has very high capacitance, that means for a given potential difference, you can have very high charges in the conductors. So this means a capacitor with large capacitance can hold a large amount of charge Q at a relatively small V. So these are the basics of capacitors. Okay, so we saw a random capacitor. Now we are going to see a more structured capacitor. So we take two parallel plates and both are conductors, and we have surface charge density is plus sigma here and minus sigma here, and we put these two conductors at a distance d, and they both have equal area A. So this is called a parallel plate capacitor. So parallel plate capacitor consists of two parallel conducting plates separated by a small distance, and the surface charge density sigma here is Q by A, and plate 2 has a surface charge density of minus sigma, again it's minus Q by A. The electric field is calculated in different regions. So there are three different regions, 1, 2 and 3. So in all three regions we are going to talk about what is the electric field. So let's first take the region 1. So in the region 1, if you see the region 1, we have to use the superposition principle and calculate what is the electric field coming from this plate and what is the electric field coming from the plate 2. So from the plate 1, the electric field is going to be outward. So it will be going up. So it will be sigma by 2 epsilon 0. Because it's a positive charge, it goes away from the plate. But if you take plate 2, it's a negative charge. So the electric field has to be going down. So, and they have the value of sigma by 2 epsilon 0. It doesn't depend on the distance. So in this region 1, we can assume that sigma by 2 epsilon naught is coming from plate 1 minus sigma by 2 epsilon 0 is coming from plate 2. So the total electric field in region 1 is 0. So outer region 2. So similarly, we will take the region 2. In region 2, the electric field coming from point 2, plate 2 is going upward because it goes towards the plate. And for plate 1 is going downward because it goes away from the plate. So again, they cancel each other. So we can say that the electric field in region 2 is also equal to 0. So what happens in between the plates? In between the plates, then see the electric field, let's take a point here and see what happens to the electric field at that point. Due to the plate 1, the field is going down. Due to plate 2 also, the field is going down because towards the plate. So then we have sigma by 2 epsilon 0 plus sigma by 2 epsilon 0 equal to sigma by epsilon 0. And what is sigma? Sigma is nothing but surface charge density Q by A. So we have Q by epsilon 0 multiplied by A. So for uniform electric field, we can define the potential difference as electric field times the distance between the plates. So then V equal to E multiplied by D. We will substitute the E from this equation. Then we have 1 by epsilon 0 Q D divided by A. So now we know E. We can easily calculate what is the capacitance of this configuration. So capacitance is already defined as Q by V. So then we have C equal to, instead of this Q by V, we can substitute V equal to 1 by epsilon 0 into QD by A. So you have C equal to epsilon 0 A by D. So one thing to note here is this C depends only on the configuration, that means the structure of this capacitor. So the area and the distance between them. It does not depend on how much charge you have or what material you use and all. So the capacitance value depends only on epsilon 0 A by D. So the note that the capacitance depends only on the dimensions of the plate and the distance between them.
Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology, for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com, contact 99402 49720.